Alright, this time around we're going to look at Lewis dot structures. Alright, so at the end of this we're going to hopefully learn how to create Lewis dot structures for any atom and any compound. We need some practice, but this should give you the gist of it. So quick review again, we're going to need to use valence electrons. Those are the outermost electrons in that outermost shell that help participate in all the bonding between atoms. Every atom wants to have a full outer shell. So their full outer shell, a full octet, should have either 8 electrons for most atoms or 2 if it's hydrogen or helium. So Lewis dot structures. It's a way we draw atoms in more detail to show how they bond, how they connect, and so we can see their structure and connections so that we can see how all the electrons are matched up together to get their octets to be full. If you want to write that down, I'll give you a second. Feel free to pause. Once we know their structure, we can determine what properties it has that helps us figure out how to create medicines and other things and create new properties and chemicals from these. Alright, so when we draw a Lewis dot structure for an atom, we need to draw dots around the element symbol. So in this case we have chlorine, Cl. We define how many valence electrons we have. So if we go look at chlorine, we realize there's 7 valence electrons. We're going to draw in 7 dots. We're going to draw on the first one. I tend to put it on top, doesn't have to. The next one's going to go on the opposite side, diagonal from it, so that's its second one. So the first 4 you draw are going to tend to go as far away from each other as possible because the electrons are negative, and negative charges are the same, and the same charges are going to repel each other. So if you have 2 negatives, just like 2 same charged magnets are going to repel each other. So if one's on top, the other one's going to go on the opposite side. Then the third one I put on the left, fourth one on the opposite, on the right side towards the bottom. After that, then we're going to start putting them clockwise. Is that counterclockwise for you guys? Clockwise around the atom. So our 5th one will go on top, 6th one on the right, then our 7th one on the bottom. Since it only has 7, we're not going to put an 8th dot because there's not an 8th valence electron. We'll do a similar thing here in a second with oxygen. So oxygen has got 6 valence electrons, so 1 on top, 2 on the bottom, 3 on the left, 4 on the right. Now we go clockwise, so 5 on top, 6 on the right, being the unpaired one on the left and an unpaired one on the bottom. Okay, if that made sense, you think you can do it, go ahead and pause now and try and draw out the electron configuration. Use those to get the valence electrons and draw out the Lewis dot structures for these 6 atoms. If not, follow me through this. Carbon's got 4 valence electrons. We're going to have 4 dots going around, 1 on each side. Looks something like that. Boron has 3 valence electrons, so we're going to get boron with 1 on 3 of its sides. Hydrogen has just 1 lonely electron, so we can put 1 up on top. Argon's got a full 8 valence electrons, so it's going to get 2 on each side in a pair. So we've got 2 on top, 2 on the right, 2 on the bottom, and 2 on the left. That's its full octet. It's all it can handle. Then helium has got 2. I may ask, why is there 1 on top and the other one on top, not 1 on top and 1 on the bottom? Well, helium's one of those exceptions. It's got a full octet at just 2. When you have a full octet, they're paired up. So helium's that way, and if hydrogen got another electron somehow, it would also have a second dot up here. Those are the weird ones because they're so small and teeny. But most atoms will fill their first one on top, second one on the bottom, third, fourth, until they get something similar to argon's Lewis dot structure. And our last one goes to nitrogen with 5 valence electrons, so 1 on top, 1 on the bottom, left, right, and a second one on top. So we've got 1, 2, 3 unpaired electrons there. It's similar with compounds. They'll look a little different, but same idea. You can start adding dots around all the elements and it'll start connecting them up to make compounds. We'll talk about how this goes in detail a little bit, but it'll look something like this down the road. It'll be both with dots and with lines, but just FYI, we'll do electrons on the elements and turn them into compounds to make a more full structure to get the properties of them. Alright, things to know when we go towards compounds. The number of electrons gained or lost by an atom, so I'm going to try and get the charge of it to form its octet. That's equal number of bonds it can make when we're doing this. So for example, carbon has got 4 valence electrons. It can have a 4 plus or 4 minus charge. Therefore, it can bond 4 times with something. Either the same thing 4 times, or 4 different things, or whatever. It can make 4 bonds total. Oxygen has 6 valence electrons. It's got ends up having a 2 minus charge. It's going to lose, no, sorry, scratch that. It's going to gain 2 electrons, and in that it can bond 2 times for those 2 electrons it's gaining. And when it does that, it can make those 2 bonds overall. So 6 valence, 2 minus charge, bond 2 times. Hydrogen only has 1 valence electron, can only make a 1 plus charge, so it's just going to be able to bond 1 time. If that makes sense, now you give it a shot. How many bonds can phosphorus make? How many bonds can magnesium make? Pause, answer, see if you're right. Hopefully you said phosphorus can make 3 bonds. It's got 5 valence, gets a 3 minus charge, it can make 3 bonds. Magnesium, hopefully you said it can make 2 bonds. It's got 2 valence electrons. It'll lose both of those to have a 2 plus charge, and it can make 2 bonds because of it. Alright, now let's look at the compounds with Lewis dot structures. We've got CH4 called methane. So in this case, we're going to write down what we know first, then we'll draw it out. So we know that carbon has 4 valence electrons, and therefore it needs 4 more to get its octet, so it can make 4 bonds. Hydrogen, on the other hand, has only got 1 valence electron. It can bond 1 more time to get its full octet of only 2, one of those exception ones, so it's going to bond 1 time. So we draw out carbon, add its valence electrons. We've got 1 on each side. We need 4 more total. Conveniently, we have 4 hydrogens. So we bring in a hydrogen with that 1 valence electron. It'll bond up here. Now we've got 2 valence electrons total for hydrogen, a full octet for hydrogen. But we need more for carbon still, so we're adding another hydrogen, and another one, and another one. Now we've got 2 for hydrogen, 2 for this hydrogen, 2 for the bottom hydrogen, 2 for the right hydrogen, and a total of 8 electrons for carbon, a full octet, which means it's good to go. Both our hydrogens and our carbon, a full octet, they are stable. That's a full Lewis dot structure for CH4. Once you have them all in the full octet, that's a correct Lewis dot structure. So once you say that, then you know that they're bonded together to make the correct compound. Okay, so once you have the elements bonded, you can substitute those 2 dots we had between the carbon and the hydrogen into a line to represent a bond. So when you see a picture something like this, and there's not just dots here, but if the 2 dots are between 2 different elements, so if there were 2 dots here between the nitrogen and the chlorine, those 2 dots can be turned into a line. The line means those 2 dots, those 2 electrons, are being used in a bond. These 2 dots on chlorine, these 3 sets of 2 dots, are not involved in a bond. They're called a lone pair. Those cannot be turned into lines. They're just used on the outside. So the ones that are between atoms, those can be turned into lines and to be shown that they're bonding electron pairs. They're attaching the 2 atoms together. Okay, so heads up, when you're building one of these Lewis dot structures for a compound, you always want to put the element you have the least amount in your formula in the center first. Draw its electrons around it, so it's Lewis dot structure. Then add the other electrons from the other elements in to make the bonds. So that's why we put nitrogen in the middle of this one. In this formula, it's NCl3. There's one N, 3 Cls, so N goes in the middle. They draw its 5 valence electrons, then start adding the chlorine's valence electrons and its Lewis dot structure together to make this Lewis dot structure for the whole compound. Okay, so sometimes you may need to make multiple bonds, so things get a little bit tricky, so try and stay with me. Sometimes when you draw this out, you won't have enough atoms to fill all the valence electron spots on the center atom, or on other atoms. If so, that center atom, and maybe others, they need to make more than one bond to other atoms around there to fill the octet. So in this case, with this molecule here, CH2O, when I drew out carbon with its 4 black valence electrons, we were good. It has valence electrons, it's got 4, it needs 4 more bonds. 1 came from the hydrogen here, that was 1 giving it 5. 1 came down here from the other hydrogen with this red dot, giving it 6 valence electrons. 1 came from the oxygen, giving it 7. So it's 2, 4, 6, 7. It needs to have 8 for a full octet. Our hydrogen's got 2, it's good. This hydrogen has 2, it's good. But oxygen also has 2, 4, 6, 7. So oxygen has 7. Carbon has 7. If they're both 1 short, they can use this lone electron on top and this lone electron on top and make what's called a double bond or another bond, and they can share those electrons both on the side here and the ones on top to make a double bond. It looks something like this when I draw it out. So now this carbon gets to use these 2 electrons for 2, these 2 for 4, these 2 for 6, and these 2 gives it 8. That's a full octet. Same way oxygen to use these 2, 4, 6, and these 2 is 8 because they're sharing all 4 of those electrons. So they all have an octet now. They're all happy, they're all content. That makes a legit Lewis structure. Sometimes it could even go to the fact that you'll have a place where, in this case, you need to make not just a double bond, but a triple bond. If you note, there's 2 open electrons, an electron here that's open, and maybe one on the bottom that's open, but there's a molecule on the left or right that's got an open one on top and bottom. You could circle one on the top and the bottom and the side pair to make a triple bond. So as you guys practice that, you'll see some of those, and you'll get more practice with those. Hope it makes sense.